This is the Calculus Pre-Lecture Series. I'm Caitlin Murphy, and this podcast is on trapezoidal approximations. First, we'll recall the definition of an integral. You can pause the video here to read the full definition, but I'm going to specifically talk about this right-hand side of our definition here, of our equation. So this right-hand side is built up from the idea of Riemann sums, which is where we use rectangles to approximate the area under a curve. So say we have a function, here we'll draw in red, here's f of x, and we'll have our interval here, here's a to b. So notice f of x is continuous and positive on a to b. Then we divide this interval up into n equal parts, and we use rectangles to approximate the area under the curve here. Okay. And it turned out in here, in this definition, that when we take the limit as n goes to infinity, so as we take an infinite number of partitions of this interval, the limit actually is the value of the integral from a to b of this function. Okay. So in this podcast, we're going to talk about another method of approximating the area under the curve, but we're going to use trapezoids instead of rectangles to approximate the area. Okay, so recall the area of a trapezoid is given by 1/2 times the height times the sum of the bases of the trapezoid. So let's draw this picture again and see how we can relate our area under the curve to trapezoids and the area of a trapezoid. So here are axes. Here's my function, f of x, and we have an interval, a to b. We'll divide this interval up into n equal parts. Okay. So remember a, we can also call that x naught, and b is also x sub n. So we have x1, x2, x3, x4 in our case, so in this case n is 5. Okay, and let's build these trapezoids. So in between x0 and x1, we have this trapezoid. We connect the top. Here's our next one. We'll just keep going all the way to the end. So if we want to approximate the area under the curve, we'll just add the area of all these trapezoids. So let's look at the area of this first trapezoid right here, all the way on the left. Okay. So the height is going to be the distance between x0 and x1, which is just delta x. That's defined for us. Then our bases are going to be the function values. So on the left here, it's f of x1, x0, and on the right, we have f of x1. Okay. So the area for the first trapezoid is going to be 1/2 times the height, which is delta x, times the sum of f of x0 plus f of x1. Okay. And if we want to find the total area, we need to add the area of each of the trapezoids. So that's the first trapezoid. We can add the second trapezoid, 1/2. Still the height will be delta x, and then we'll have f of x1 on the left and f of x2 as the endpoint on the right. And we'll keep adding them up like so until we get to the last one. We'll have 1/2 delta x, and then we'll have f of x n minus 1 will be the second to last, plus f of x n. Okay. And that'll be the area of all those trapezoids. So let's simplify a little bit. Notice that I have this 1/2 delta x piece in each of my terms. That's the 1/2 h piece, so I can factor that out. So we'll simplify here. We have area is equal to 1/2 delta x times the quantity f of x0 plus f of x1. That came from our first trapezoid. And then from the second trapezoid, we have f of x1 plus f of x2. And keep going until we end up with f of xn minus 1 plus f of xn. So we're going to simplify one more time. Notice that on these inside trapezoids, they share one of their bases or one of their heights. So for instance, in the first and second, they share this f of x1. And that's going to be true of all the interior points, just not the endpoints. So we'll simplify one more time. We can simplify this to say 1/2 delta x times the quantity f of x0 plus 2 f of x1 plus 2 f of x2 so on and so forth until we have plus 2 times the second to last one, which is f of x n minus 1, and then just 1 of the last base, which is f of x sub n. And that is our formula for taking trapezoidal approximations of the area under the curve.